Got it.
Here's your answer.
In case you are having a doubt. So, let's wait one more minute. All right, let's get started. It's a great pleasure to give you Nikolay Gnezdilov. Did I got it more or less? Thank you. Who's visiting us from, well, formerly from Dartmouth College. He's a research, he lives in Brooklyn actually. He's a research associate in the group of Rufus Boyack. And he's been working on a number of very interesting problems, ranging from thermalization and transport to superconductivity. And today he's going to tell us about his work with Rufus on electron-boson superconductors.
Thank you very much. I'm glad to be here. Thank you for the introduction. So today I'll tell you some of our recent work with Rufus Boyack from Dartmouth, where we studied strongly correlated electronic systems, actually electron-boson systems, and some superconductivity in it within the Migdal-Eliashberg theory approach. So, why slide? Is it changed? Now it's changed. Okay. So first, let me start with Migdal-Eliashberg theory. Migdal-Eliashberg theory is a theory that explicitly accounts for the boson dynamics. Well, originally it was a phonon in the superconductivity problem, and that makes it much wider applicable than the conventional BCS approach. So when I say that the theory accounts for the boson dynamics, usually, at least in the original Migdal-Eliashberg formulation, it goes hand in hand with the adiabatic approximation, which means that you consider your boson to be much slower than your fermion, which makes sense if you compare phonon and electron, and you can consider some characteristic energy scale, say the Debye frequency and Fermi energy, or you can compare the Debye frequency and the fermionic bandwidth, or you can compare boson mass and fermionic bandwidth. Here I will use the Debye frequency and the fermionic bandwidth. And if you do so, in principle, you can consider even rather strong electron phonon or electron boson coupling. However, it comes with some limitations usually, and usually we don't have very strong electron boson coupling. But you can go formally to, let's say, lambda infinity limit, where lambda is my electron boson coupling strength, if some parameter which I am calling lambda e, which equals electron boson coupling strength times the adiabaticity ratio, the ratio of the Debye frequency Fermi energy, is small. So you can put your lambda to infinity if your adiabaticity ratio goes to 0. And then actually, since kind of early days of Migdal-Eliashberg theory, it was shown that TC diverges as a square root of electron phonon coupling if electron phonon coupling is small. But this is not something that anyone has seen in experiment. And usually it is argued that this limit, in this limit, Migdal-Eliashberg theory might be not applicable because of the vertex corrections, which I will talk about several slides later. But nonetheless, there is this theory result. On the other hand, when I say that the boson is small, it implies that in the propagator of a phonon, well, here I'm talking about electron phonon superconductivity, the effective propagator of the phonon doesn't have a self-energy part that comes from the self-consistent account of the electron-phonon interaction. Instead, this is just an effective propagator which has some frequency dependence, but this is defined, let's say, empirically. So some recent interest of this approach was generated some time ago in connection to strongly correlated electronic systems, because one can see that Migdal-Eliashberg theory works as an effective theory for strongly correlated electrons in the vicinity of the quantum critical point, where your electrons are coupled to the order parameter, electronic order parameter, which happens to be a scalar boson. And this is kind of the systems that I'm going to have in mind in this talk. So that's why everything that follows is about electron boson rather than electron phonon. Here is the difference. It's some effective approach to the electron case. So now this is going to be about some toy models, because there are several approaches how you deal with strongly correlated systems. Those are usually quite complicated, and one thing you can do very smart and complicated numerics, or you can try to come up with some toy model to capture some feature and some observables, and that's what this is going to be about. So I'm going to talk about some particular type of toy models. It's called Y-SYK models, and I'm going to explain what this is in a minute. But considerations of this type of theories, it allows you to generate observables, transport observables, and thermodynamic observables like heat, like specific heat, and from transport resistivity for the strange metal materials, which I claim to not have well-defined quasi-particles description. And these features can be captured with this type of toy models. So here is the Yukawa-SYK type model in 2D, Y-SYK model. It looks pretty simple. So you have your fermions coupled to bosons in a Yukawa fashion. But the coupling constant is drawn from random Gaussian distribution with zero mean and finite variance. And here, for this particular model, I will consider the case where the correlation, the spatial correlation between coupling constants are proportional to the delta function in the real space. And importantly, that every, let's say, realization of this coupling is independent from each other. So it's just sampled from Gaussian distribution. So what is the advantage of all this? The advantage of all this is that this kind of models, they're actually solvable in the large n limit. So if you consider a large number of fermionic flavors and bosonic flavors, and you put them to infinity, you can actually solve your model for arbitrary coupling. And later on, I will explain that there is no vertex correction. Eventually, it allows you to get your answer for any coupling. Because before I was saying you that in conventional Migdal-Eliashberg approach to electron-phonon system, there may be some restrictions on the coupling strength, and there is this divergence problem. So how it goes in a theory, which on the other hand may be interesting to get some strange metal observables, but on the other hand, it allows you to compute observables for any absolutely arbitrary coupling strengths. So these types of models, they have been studied also in zero dimensions. So let's say quantum dot case, where there is no spatial structure, or the spatial structure is ignored. And actually it was shown that for electron boson coupling going to infinity, the critical temperature is constant. So there is no trace of any divergence with respect to increase of the electron boson coupling constant. So the question is there something special about this class of models? or this is just a feature of quantum dot consideration. So what will happen if we still consider this in 2D, like it was done in the transport calculations above, but we look at the critical temperature as a function of electron-boson coupling constant, and that's what this is all about. Now I will become more technical, so I'm not sure if everyone is familiar with SYK models. So here I will give some slides how to deal with this and how to construct a large N theory with this. So as I said, the easy part about this model is the Gaussian sampling of the coupling constant. So suppose you have this V in your effect, in your action, in your theory, and then you average it out with respect to realizations of this coupling constant. And this is actually very easy if you say that J and JL are distributed from Gaussian with 0 million finite variance, because this is all just evaluating a Gaussian integral. So you're completing a square. And this is what it becomes. So I'm just completing a square. There is not much complicated about this. So I have twice, I have two fermions here, and they're doubled here, and I have the same here, and Hermitian conjugated. And I have some bosonic operators here. And here I have the delta function in real space that I introduced earlier. So this is your effective action. You may say that, well, it looks more ugly than it used to be. But actually it's not, because now you can do another trick, and you decouple this interaction, because now you can say that you have 4 fermion times 2 boson interaction. You can decouple them using Lagrangian multiplier trick, and that's how it's done. So you introduce some fields which are sigma, j, phi, f, phi, d. So far, those are just bilocal fields, but at the end of the day, they happen to be self-energies and Green's functions. So that's how this is defined, and this is defined in accordance with the definition of the Green's of the corresponding Green's function. So you just rewrite this part with respect to this definition, and of course you also take care about this term sigma and j, and phi and f, and so on and so forth, and you end up with a pretty nice set of equations in the large N limit, because in the large N limit I rewrote my action, and then I take variation of that action with respect to those fields, and that's what I can do in the large N limit, because there is a large factor of N in front of my action. And that's what it is. So for the normal sector, I get this equation for the electronic self-energy, and this equation for the bosonic self-energy. And those are equations for the Green's functions. What is peculiar about it is, and what I'm going to use here, and that's why it is kind of simple, is that because we had a spatial delta function in the theory, the momentum integrals factorize here. So actually the small g and small d are closed momentum integrals of the true electronic and bosonic propagator, and you actually can evaluate them. And this part is the linearized gap equation. Again, I have the momentum factorization here, and from this equation, eventually I should be able to compute the critical temperature. So I just mentioned that there is a factorization of momentum, which is nice, but if I look here, and one more thing is, because the factorization of momentum, because there is an integral here and here, my self-energies of electron and boson, they actually don't depend on momentum. And that's quite simplification, because now I can integrate this out. For the electronic part, I'm going to use infinite bandwidth approximation, saying that I'm just going to integrate from minus to plus infinity, saying that this is set by some superior energy scale, which is much larger than temperature, the Debye frequency, or Fermi energy. But for the boson, actually, the integral is divergent, and I need a UV cutoff. So one thing to deal with the UV cutoff is to deal with the UV divergence is to introduce the UV cutoff, and this cutoff here I will call the Debye frequency. Overall, this is just an analog of Debye frequency, but this is my UV cutoff. Another important observation is actually that here we are considering massless boson, so that's to give our problem a bit of a critical flavor. So what is going to happen with this? If we compare this set of equations, and those are exact equations, those are not perturbative, those are exact and the Largian limit. And if I compare it with the original paper by Migdal from 1958, I see more or less the same equations, up to one crucial difference that makes things simpler. So in the original Migdal and then Migdal-Eliashberg problem, there is this entity gamma, and this is a vertex. And even though the equations are similar, you actually have to treat them perturbatively, and this is a whole state of art to derive this gamma thing, because it obeys its own separate equation. So it's a much harder problem in principle. But if you compare this to this, what you will notice that there is no gamma there. So those are exact non-perturbative equations, and your gamma is just given by J squared. So there is no vertex correction there, and this is a non-perturbative thing. And again, that goes in the direction that eventually I can solve this equation for arbitrary value of electron-boson coupling. So here, electron-boson coupling is this constant J squared, and there is no limitation, which usually arises due to effect of this gamma. So it's all about when your contribution to gamma becomes large enough so that the theory will behave differently. Here, there is no this question. Right. So now, let us just evaluate those integrals, because if I integrate out this entity in the infinite bandwidth limit, it's actually a very easy integral. And it does not depend on the particular form of the self-energy which you have. It only requires the notion that your self-energy is a sole function of frequency and momentum, but this is precisely the case here. So, and then it's a very simple pole integral, and the sign of your self-energy just follows the sign of omega. This is it. And that gives you a signum function of frequency for the effective propagator that enters your self-energy. Using that, you can compute the boson self-energy, which is this one. Again, I just substitute this to there. And I see the linear and frequency behavior. So fine, there is no mass contribution here. So again, this is exact in the Largian limit. So it's equivalent to summing all possible diagrams up to 1 over n corrections. So we can do this, and we can do the same for the bosonic propagator, which is this one. And this is a log function. And here fun begins, because depending on which term inside the log is dominant, you can get different type of behaviors. But in principle, this is the propagator that describes the theory for arbitrary coupling strings. So I have this linear frequency contribution here, and I have the quadratic frequency contribution. This one is in units of Debye, and this one is in units of the Fermi. And for the linearized gap equation, I get those. And those are becoming more familiar if you've seen Eliashberg theory before. So here I just redefined my electron-boson coupling in a more standard way so that I get this type of equations. And that's what I'm going to solve here. So as I said, this can be done for any lambda for this particular theory. This is my problem. But what I can say immediately by just looking at the form of the propagator, maybe it was here, it is here. So if I substitute this propagator here, there is a problem about the frequency where the frequency omega and omega prime match. Because then I have 1/0 divergence inside the log, and this is bad. But actually, you can fix it by removing the resonance term, n equals n prime, from the equation. And you can actually show if you substitute this equation into this equation, the combined equation will look like this. And because of this factor, n equals n prime actually makes this part 0. So there is no contribution from the resonance term, and you can safely exclude it. And yeah, there is no contribution from this, so there is no divergence whatsoever here. And those are our new equations. I defined them in the positive n space because this is easier. That's how it looks like. This is my new Z, analog of quasi-particle residue, without the part that captures the divergence. But again, for the parent problem, it doesn't matter. So I'm going to solve this set of equations. How should we do this? So this is a linearized gap equation, which tells us that is basically a eigenvector eigenvalue problem. So you can find your critical temperature from solving a determinant equation, where the thing that acts on your delta is a matrix. You need to find the determinant of Z minus identity matrix. And from that determinant, you look for the place where the determinant gives you 0. And this is your lowest eigenvalue. This is the critical temperature. Again, this determinant method that was pointed out by Gresin in '87, and that's what I'm going to use here. And it goes actually quite handy because usually when you try to solve this problem, for example, in weak coupling, well, weak coupling means if I have some intuition, for example, from BCS, then I get my critical temperature to be exponentially suppressed, which means that I have to go to very low temperature, which means that I'm going to have a very large Matsubara grid for the things to converge. Here, I'm first interested in the asymptotically strong coupling, which means that this parameter lambda e goes to infinity. And you can solve this eigenvalue problem just relying on 3 frequencies. So a grid of 3 positive frequencies is actually sufficient. You can do 100, you can do 1000, it doesn't matter. The answer will be this. So we solve the eigenvalue problem for this one. We solve the determinant equation and find that TC is independent of the electron-boson coupling, which is good because we took lambda to infinity limit. So there is no divergence here. But we see that TC is some fraction of the fermionic scale in this case, the Fermi energy. And from the structure of equation, actually, one can see how lambda cancels, because if I look at this propagator, and as I said, there is no contribution from the term where bosonic frequency is 0, then making this lambda e to infinity, I can say that this term is dominant over this one, and then I can expand the log, that's what it is, and then this lambda cancels with this lambda, and then cancels this lambda, and so on and so forth. So your whole pairing problem is independent of electron-boson coupling. So to give some more background, maybe, in the strongly correlated electrons, there is this class of models called gamma models, introduced by the group of Chubukov. And what they do, they describe strongly correlated electron-electron systems in the vicinity of the quantum critical point. But they describe it in such a way that they define by hand some particular form of the effective interaction, and that effective interaction is dynamic. So it frequency dependent. And usually it has this type of form where this gamma can take different values. But again, this is not something self-consistent. This is something they just assume that suppose my effective dynamic electron-electron interaction behaves in this way. And what is funny about this, that in this asymptotically strong coupling limit, the pairing problem exactly coincides with their gamma-1 result. And the answer, again, coincides with what they get for that particular class of quantum critical systems. In principle, this, let's say, saturation of TC, it appears just from the fact that for suppose your bosonic self-energy is proportional to your coupling constant, which is the case for this equation. But I can come up with other types of this type of Magian models, where again I will have J squared somewhere here, which means that this term is dominant. And if this term is dominant, again you can substitute your bosonic propagator in the electronic self-energy, and that cancels the coupling constant. So it's just that. So it's about having your bosonic self-energy to be the dominant contribution in the asymptotically strong coupling. And what I said in the beginning is that usually in the conventional Migdal-Eliashberg approach, the self-energy of the boson is neglected. But here, because you can go up to arbitrary coupling, you can go up to the regime where actually that self-energy is dominant, and that cuts the divergence in TC and makes the TC finite. So suppose now I consider a limit. Oh, okay, here is the solution for TC. So I just sketched how we did analytical calculation with 3 frequencies, but we also solved this equations numerically with the exact propagators without doing expansions and so on and so forth. And so you can go to absurdly large lambdas. And what you see indeed that you saturate this bound. So you cannot go higher than this. And depending what is your adiabaticity ratio, you can achieve this bound slower or faster. So suppose I have my adiabaticity ratio very small, then I will achieve this bound somewhere at very, very large lambdas. Or in the opposite case, where my adiabaticity ratio is, let's say, order one or larger, then actually the saturation happens quite quickly at lambda being of order 1. So let me see what happens. So this one is TC in units of Fermi energy. And so we computed this part, and it coincided with our estimate. What happens here? And this is a strong coupling case. So suppose I consider like a conventional Migdal-Eliashberg setup in the strong coupling where lambda is very large, but my adiabatic ratio is very small. Again, it boils down to solving the same equation for the determinant. But what we can see from there is that if I rewrite my bosonic propagator in this way, I have a new small parameter. And the small parameter is my adiabaticity ratio. And what I can make happen here is that this term will be dominant above this one, which is the bosonic self-energy. And then again, I can expand the log. So in this limit of coupling where EF over omega Debye is a very large entity, you can ignore the bosonic self-energy and recover the older result known from the Migdal-Eliashberg theory. So yes, we just found it. Again, it happens for the case where you can consider strong coupling, but still you're neglecting the boson self-energy. when you look at how the pairing problem is formulated, and we're dealing with massless bosons and so on and so forth, once again it maps onto some type of these gamma models of quantum critical systems, but now it maps onto gamma equals 2 here. So that's what it is. And again, this is happening within one model. So in original gamma models, you just set up your interaction strengths to be, sorry, your effective dynamical interaction to be some power law, which you just assume here. It comes in a self-consistent way. So you can tune your lambda, and within one model, you can have different type of behavior. And then up to the normalization of your coupling constants, so if you compare to them, you recover this 0.18 result known for quite some time. So what is happening is, if you look at TC versus lambda, and if you're in the adiabatic regime where your boson is slower than the fermion, indeed, first you have this divergence, but at much stronger coupling, depending on your adiabaticity ratio, your divergent TC must saturate to some constant value. And that's how it looks like. Now, let me draw TC as TC in units of omega Debye. Again, if I look at this region of coupling, so this is my analytical prediction, that's how it should be. And the dotted plots are is my numerics. So for this part, so this is an adiabatic, still an adiabatic curve where omega Debye over F is very small. A large portion of this behavior is square root of lambda. But then you see that here it becomes, it begins to deviate from the square root of lambda thing. And to see this deviation, you need to go, when you go to very large coupling, actually this is a place where the boson self-energy becomes important. If you go to the non-adiabatic case, then the square root behavior is absent. But you can say so, maybe you can maybe say that when omega Debye over EF is order 1, it means that you just have one energy scale in the problem. So you don't have a competition between bosonic and electronic scales, and then it resembles what happens in 0D. But what is important here in 2D is that because we incorporated the momentum structure of the theory, we now have two scales. And when we look for omega Debye over F being in the adiabatic region, we can recover this long-known square root divergence, but also we see that it's not actually a divergence, and later on it's saturating. So in principle, both regimes are present. So it's a matter of a scale of lambda, where you go from one regime to another, and they, as I said, correspond to a different type of critical behavior in the purely electronic manner. Now I can go to weak coupling. Again, it's very much the same story, but now very weak coupling. In the weak coupling case, of course, I cannot expand the logarithm. I should keep this logarithm because nothing is small there. It's actually pretty large. Yes, this one. So I cannot expand because this one is very small, and temperatures are presumably also very small. So all these things are small, you cannot expand. So you have to keep the log. And numerically, actually, this regime is a bit more complicated because you're looking at small temperatures in the end of the day. So you need to have much larger grid, and instead of being fine with few frequencies, you have to go to hundreds of those. But this is still doable. And what you find is that, so we're considering massless boson. And for the massless boson, we get TC to behave as an exponent of -1 over square root of lambda. So usually in the let's say BCS case, you have 1 over lambda there, but this is a square root. But this is again something that has been observed for, well, has been predicted for massless bosons some time ago. And funnily enough, it also corresponds to this gamma equals 0 plus case, where the effective electronic propagator is logarithmic. Effective interaction is logarithmic of the critical gamma models. So that's where you get the square root behavior in the exponent. So what was this all about? To summarize, is that the Migdal-Eliashberg theory, it applies to a related electronic system near quantum criticality. And again, as I said, this is a setup where the effective electron-boson interaction, it appears from electrons being coupled to some electronic order parameter, which behaves as a scalar boson. So this particular setup, the 2D setup, is self-consistent and solvable in the large limit version of Migdal-Eliashberg theory with no vertex correction. That allows you to explore all possible values of coupling, literally go to infinity without the fear that vertex correction will break down the Migdal-Eliashberg theory. So because in contrast to a conventional Migdal-Eliashberg theory, we have an access to all range of couplings, we can see that indeed for some intermediately strong coupling range, there is the square root behavior, which was predicted long time ago, but then it crosses over to the saturated value, which becomes some fraction of the Fermi energy in the end of the day. So we can, in principle, try to estimate, okay, we get this fraction of Fermi energy, and we compare it to something, because, as I said in the beginning, there have been some works which apply this type of analysis to get some transport and thermodynamic observables in strange metals like resistivity or specific heat. So suppose I get some parameters from the experiments they're trying to compare and estimate what kind of TC I'm going to get here. And if I do this, I get TC order of 100 Kelvin. And this is what it is. And also, different types of these coupling regimes, as I said earlier, they correspond to different types of quantum critical electron-electron system within just one model, all self-consistent. So you don't have to engineer this dynamical electron-electron interaction. It just appears in self-consistent. So this is it. Very nice. Thank you. And
right, now time for questions. If you're in the online audience, feel free to unmute yourself and ask directly. Any questions? Yes, I mean. Yeah.
So in this work, can you also look at how TC would depend on magnetic field, like with this approach, external magnetic field?
You can, but that's not something we looked at. In principle, one can look at it also.
Yeah.
Okay. Yeah. So I think in the original, I think the 80s paper, there was this gamma term, which you said that is ignored in large N limit. So like I didn't fully connect that. Why is that gamma term getting ignored?
Yes. By gamma term, you mean the vertex?
Yes.
So let's compare it. Just two set of equations. So here is the Migdal equations, and here is your gamma term. So this is your expression for the electronic self energy. So G times D. And that's what it is, G times D. Well, there are small d and g's, but that's because of the factorization of momentum. It's literally the same expression up to the factorization of momentum. So here you have this gamma thing, which should be determined from its own beta salpeter type of equation. Where is it here? It's actually not here. So there is just constant. So if you compare here and here, there is no this term. If you want a more sophisticated answer, if you look at the diagrammatic structure of this expression, there are no cross diagrams. And that's what happens in the Largian limit. And usually those, they give rise to this vertex, but they're not appearing in the Largian limit.
Like, how does the structure of diagrams depend on the, and like saying that they don't exist in Largian?
Right. It's a very simple diagrammatic series.
Like, they don't exist, or are they getting suppressed by like
They're
the other?
suppressed by 1 over n, but you put n to infinity. In principle, it should exist, right? But again, I said it's a Largian theory. The power of Largian theory here is that you suppress all kinds of diagrams that makes life more complicated. This is also the case for pure SYK model. So in the SYK language, where you have just 4 fermions, and you also have, you apply the same machinery, diagrammatically, what you see is that your diagrams are only melons. And the parts of the melons, they don't talk to each other. So you just have a whole bunch of melonic series. And as I said, those are non-perturbative equations. So this sigma g's these, they're exact Green's function in the Largian limit, meaning that I summed all possible diagrams that contribute in the Largian limit.
Yeah. My second question is that you were dealing with massless bosons.
Yeah.
So, like in particular, like, are you looking at like phonons or other types of bosons as well?
So, as I said, this is not about phonons. This is rather about electron-electron systems near quantum criticality. That's why we consider things massless. In principle, one can consider something massive. So in the strong and asymptotically strong coupling limit, I would not say change much, because still you have a dominant term which comes from the electronic self-energy. But maybe there can be a contribution to the bosonic self-energy, itself.
Yeah, that's what I was thinking.
But here it's purely massless and it does not appear. So there is no mass generation of the boson.
So like, what's like the ideal like origin of bosons? Like phonons you can have like from the lattice, but like if you're considering like arbitrary bosons, so like what would be like the experimental like candidate for that?
So again, this is a toy model, but the inspiration behind this is as follows. So you have an electronic system near quantum critical point, and there you have some other parameter, for example, pneumatic. And then your effective theory would be electrons coupled to this other parameter, which is an electronic other parameter, but behaves as a scalar boson. So it's not an electron phonon situation. As I said, so this is Migdal-Eliashberg applied to electron-electron system, where electronic order parameter behaves as a scalar boson.
So with this framework, can you explain as you said, like pneumatic orders, like in strongly correlated superconductors, like for example, YBCO, that like after the phase transition, like the other orders, like how would they react to the superconductor order arising?
Well, I think it requires some preliminary knowledge of where this theory comes from. You then have to mimic your pneumatic order by something. This is just a toy model consideration that I have some massless boson in the game. So in principle, people claim that they restore some of the observables of this type of materials. But usually, as far as I know, in this kind of framework, this is mostly about computing resistivity or specific heat. I don't know on top of my head if anything more than that has been done.
I've got a very naive question. You go to the conclusion. What's you said that like so here you say that for the 2D Y-SYK model, what does it mean 2D Y-SYK model? I mean, I thought that, I mean, my naive interpretation is that the SYK model is infinite dimensional in a sense.
Yes, you can say, okay.
So what's the dimensionality you're talking about?
Yes. Let's go to the definition of that. So here you see that there is some spatial structure sitting here in principle, but it matters what I write next to it. So here I can write some fermions and bosons. And by 2D, I mean that I will write fermions with dispersion and bosons with dispersion. So it means that you may think of a lattice, and then on each lattice side you have this type of interaction, or maybe you have this type of interaction everywhere. So it depends on your consideration. A purely zero-dimensional case, then of course it's just one dot and you have no dispersion. So this type of results that I just shown there, they appear, and this crossover, it appears, crossover in TC, because we accounted the dispersion of fermions and bosons. In principle, you can say that this effective theory is still effectively zero-dimensional. And that would be true because some integral, I evaluated some integral, but still some of the spatial structure is incorporated in that. Because if you don't have that, you just don't have the scales. So there is nothing to set your Debye frequency in 0D. And there is nothing that sets your bandwidth and so on and so forth. So that's where dimensionality actually plays a role. So this psi and this bosonic dispersions, they are important.
So Mehdi, feel free to unmute yourself and ask directly.
Okay, hello. So actually I have two, do you hear me by the way? I mean,
Yes, we do.
So, okay, good, thank you. So I have two questions. First is that, do you have some numbers for TC, you know, well, for some known materials, for example, you know, the heavy fermion material close to quantum criticality of whatever number that you know, probably. Do you have?
Yes.
This is the first question. And maybe the second question is that, so if I understood correctly, actually I joined a bit late actually because I'm living in the, you know, different time zone actually. So if I understood correctly, you use your model for phononic system, right? I mean, omega d is the Debye frequency. Then my question is that, can I use the same formalism for, you know, a metallic system close to some ferromagnetic or anti-ferromagnetic quantum critical point or something like that? Then what would be the, you know, the analog of the omega d there on this Debye frequency there?
Right. So here the Debye frequency appears as the UV cutoff. So it's not like a literal Debye frequency of an electron phonon system. It's some UV cutoff which I need to regularize the bosonic propagator. So it's an analog of that. But this is a characteristic scale in the bosonic sector that I have to introduce because my theory is massless. For example, if I would have a massive boson, then I would probably use that scale. But here, as I said, to define my propagator and avoid divergences, I need an upper cutoff, and I use that upper cutoff, and I call this Debye frequency. But maybe this calling it a Debye frequency is a bit misleading because it's not related to an electron phonon problem. It's about electron-electron case, but I just call this UV cutoff to be the Debye frequency. So that's why I said it's not in the beginning I said like it's not a Debye frequency, it's an analog of the Debye frequency, which is used to set up the UV energy scale for the boson. Speaking of the TC in strange metal materials, again, so the TC that we're predicting here, because in the end of the day we're solving just a linearized gap equation, it's about constructing some type of upper bound. It may be not actual TC, right? It's an upper bound, so you have to be below that eventually. And again, we did some type of comparison. Some other people are doing in the field where they compare transport or thermodynamic properties to some experiments in strange metals. So using the parameters from the same experiment, we evaluate this upper bound, which is of some fraction of Fermi energy, to be like 100K. And I think for the same material, you get order like 40 or 50 Kelvin, the actual TC that has been measured. But of course, it heavily depends on the doping fraction. But for the same doping fraction, I think, so this bound is above the actual observation. But that's kind of the point of it, because it's a kind of an upper bound for this type of systems, rather than like actual sure TC.
Okay, thanks, Adrian. Thanks, Nikolay.
Sure, of course.
I have another question. When you computed the effective action, I think you ignored some of the 4, I think, boson and electron terms. Is that correct?
No, it's not correct. I don't think I wrote actually the effective action here. I wrote just the variational outcome out of it. Oh. So this is your effective, this is your interaction, right? What I have to do, I have to take a Gaussian integral with respect to constants. And this is not a complicated exercise. This here is my Gaussian integral. It looks long, but it's not that complicated, because now using this Lagrangian multiplier trick, what I do is I call this object, it becomes, what it becomes? It becomes D, where is D? D is here, it becomes D coupled to G squared, right? And the same here. And then you also have terms in your effective action, which are sigma dot G, phi dot F, and so on and so forth. So in the end of the day, your effective action using this trick becomes free of the electronic operators. And this happens because, well, first of all, you have these electronic operators here, but they contribute to the, let's say, quadratic part, where you have psi psi or phi phi, and inside there is like d tau minus psi plus or minus corresponding self-energy. And then you integrate out with respect to fermions and bosons, which gives you some logarithms of determinants. And at the end of the day, your action is just sigma G dependent or phi D dependent or phi F dependent, but there are no fermionic operators anymore in the effective action. And because you have like large N in front of it, you do a variational approach. So you make a variation with respect to all those bilocal fields, which leads to this type of saddle point equations. So it's a saddle point, but there are no fermionic operators. We're not ignoring something because we don't like it. We actually account for everything. If you're interested, I can show you in more details how it's done.
Yeah, Nikolay is going to talk to Yasamin next, and you can talk to him after if you want. Thank you. All right, no more questions. Let's thank Nikolay one more time. Thank everyone in the audience.